Hello everyone, welcome to our seminar project for the course ME 221 Structural Materials. So, topic covers are introduction and problem statement and motivation, the scientific principle of X-ray diffraction techniques, early methods such as law method, powder diffraction methods, diffractometer techniques, the current state of this art, and applications of XRD. Challenges and future trends will be the conclusion of our X-ray diffraction techniques. Introduction. To understand materials' atomic structure, we need to identify crystal phases, measure stress, characterize nanostructure, but many techniques alter or damage the sample. The elegant solution is X-ray diffraction. XRD is a powerful tool and completely non-destructive technique that helps us understand the atomic structure of materials. By shining X-rays on the sample and observing the scattered pattern, we can measure the spacing between the atomic planes. The story of XRD began in 1895 when William discovered the X-rays. In 1912, Max von Laue proved that crystals can diffract X-rays, a breakthrough that opened the door for crystal structure determination. Just a year later, in 1913, the father-son duo formulated the elegant Bragg's law. N lambda equals to 2d sine theta. This simple equation relates the X-ray wavelength, the interplanar spacing d, and the diffraction angle theta. It becomes the foundation of modern crystallography and earned them the Nobel Prize in the physics. Now, the today's materials are becoming more complex, miniatured, and multifunctional. This creates several challenges for material scientists. So, the motivation is we need to identify different crystal phases in multi-phase systems. So, now we know XRD is important. Let's look at the scientific principle behind it. X-rays are a form of high-energy electromagnetic radiation with wavelengths comparable to the spacing between atoms. When an X-ray beam strikes a crystal, its oscillating electric field makes the electron inside the atom oscillate at the same frequency. This oscillating electrons acts like tiny antennas, and a process known as coherent scattering is going on. In a crystal, waves scatter from billions of atoms overlap with each other. In some direction, they line up perfectly, giving the constructed interference. That is, n lambda equals to 2d sine theta by Bragg's law. But sometimes they give up to a destructive interference, like cancel out each other. To perform XRD, X-rays are first generated by bombarding a metal target, usually tungsten, with high energy electrons inside the X-ray tube. The resulting X-rays are directed onto the sample. A detector is there, then records the intensity of diffracted beams at different angles. The result in a graph of intensity versus 2 theta graph, called as XRD pattern. Each peak in this pattern corresponds to the specific set of crystal planes that satisfy Bragg's law. The position of the peaks reveals that the interplanar spacing, that is d spacing DHKL, and the intensity of the peaks tells us about the arrangement of atoms and the relative phase composition. So, this is how XRD converts scattered X-rays into structural information at the atomic scale. Thank you.
Hi, I'm Ankit and I'm going to tell you about Lawes method. It is one of the oldest methods. It uses white radiations and the scattered beam is recorded on photographic films. These photographic films are known as Lawes photograph. These Lawes photograph contains Lawes spots, each of different wavelength, and the shape of the spots depends on the beam. It depends on the type of the beam of X-ray. If the X-ray beam is parallel, the spots are small and round. If the X-ray beam is divergent or convergent, the spots will be elliptical or line-shaped. The Lawes method are of two types. First is the transmission Law method, and the second is the back reflection method. Back reflection Lawes method. In transmission method, film is behind the specimen, and in back reflection Law method, a film is in front of the crystal or the specimen. The beam is passing through the crystal and it gets reflected back and recorded on the film that is present in front of the crystal. That's back reflection Law method. Back reflection Law method is primarily used for thick crystals, or if you want to know about the orientation of the surface of the crystal. Whereas the transmission Law method is basically used for thin crystals, and if you know about the information about the entire volume of the crystal.
Now I'll talk about two of the earliest X-ray diffraction methods, the rotating crystal method and the Bragg spectrometer. The rotating crystal method, developed by the Bragg in 1930, was the first precision diffractometer. A single crystal mounted and exposed a monochromatic X-ray beam. While the crystal or detector is rotated, this allowed direct verification of Bragg's law and accurate measurement of interplanar spacing. It laid the foundation of modern crystallography. However, it was limited to single crystals, required very precise alignment, and was quite time consuming. On the other hand, the Bragg spectrometer works on the similar principle, where a monochromatic beam strikes a crystal and diffraction arcs are recorded on a cylindrical film. Each arc corresponds to a particular lattice plane. This method is especially useful for determining unit cell dimensions, symmetry, crystal orientations, but again, It only worked well with perfect single crystals, and the intensity data was not very reliable, so it was unsuitable for polycrystalline samples. Together, these methods gave us the first quantitative way to study crystals and set the stage for the powder method and later diffractometer techniques.
Okay, now we are talking about powder X-ray diffraction techniques and its variants. First, we'll talk about the Debye-Schramm method developed in 1915-16. It was a breakthrough because it allowed crystallographic studies on powdered sample instead of requiring a large single crystals. In this method, a finely ground sample is exposed to monochromatic X-rays, producing concentric diffraction rings. These rings act like a fingerprint, making it possible to identify crystalline phases and determine unit cell dimensions through Bragg's law. Over time, several refinements include the accuracy, the Siemens-Bromel geometry, enhanced focusing and resolution. The Guiner camera used monochromatic beams for precise lattice parameters, and the pinhole or microbeam techniques enabled analysis of very small or heterogeneous samples. Today, powder diffraction remains the universal technique for polycrystalline materials because it needs minimal preparation, works with diverse samples form, and is relatively fast and is non-destructive, making it indispensable for material characterization.
X-ray diffraction works on a very simple idea called Bragg's law. When X-ray hits the crystal, they bounce off the atomic planes, and at a certain angle, they add up to give strong signals. By measuring these signals, we can understand the arrangement of atoms inside the material. The instrument has a few key parts: an X-ray source, some optics to control the beam, a simple holder, a goniometer that changes the angle, and a detector to record the data. The workflow is just like taking a fingerprint of the material. First, we prepare the sample, then we set up and calibrate the instrument like scaling up to 0, then collect the diffraction pattern, clean the data, and finally analyze it to find things like phases, lattice spacing, grain size, or residual stress. That my friend's gonna explain you in the further slides. XRD is very useful because it is non-destructive and gives a lot of information. However, if the sample is not crystalline like amorphous, its peaks overlaps and the results may not be very accurate.
Now let me give a quick overview of latest advancement in X-ray diffraction. First, high resolution XRD gives extremely precise measurements on strain, lattice mismatch, and film thickness. This is very important for semiconductor devices where even tiny changes affect performance. Second, grazing incidence XRD looks only at the top few nanometers of the material. It's great for studying thin film coatings and surface treatments without interference from the bulb. Third, synchrotron XRD use powerful turnable X-ray beams. This allows real-time studies of materials while they are working, like batteries during charging or catalysts during reactions, capturing even very fast changes. And finally, new trends in include faster reciprocal space mapping, AI for phase identification, combining XRD with electron microscopy and neutron diffraction, emerging tools like portable devices and ultra-fast femtosecond XRD. In short, modern XRD is now more precise, faster, and smarter, helping us understand materials from atomic scale to real devices in action.
Now we will be talking about the applications of XRD. First, we'll start off with residual stress and texture analysis. At its core, XRD works on Bragg's law, and any stress inside a material shifts the spacing between lattice planes. That shift shows up as a movement in the diffraction peak position. So essentially, the crystallites themselves are acting like tiny strain gauges. Now, when a material is stressed, its crystal lattice deforms elastically. Even very small changes in the interplanar spacing, on the order of picometers actually, can be picked up by XRD. Because the penetration depth is only about 5 to 30 micrometers, XRD is especially useful for looking at near-surface stresses like those introduced by machining, welding, or coating, or any such processes. Residual stress analysis with XRD often uses what's called as the sine square psi method, where we tilt the sample and measure peak shifts. With the right elastic constants, we can back calculate the stresses. There are also more advanced methods like the cos alpha approach, which is faster and less sensitive to texture. Now, texture analysis is a related idea but looks at how grains are oriented rather than strained. Preferred orientation or texture affects properties like strength, ductility, and magnetism. We can measure this using pole figures or orientation distribution functions and techniques like GIXRD, which is grazing incidence XRD, and especially useful for thin films. Finally, in terms of measurement approaches, lab XRD gives very precise results, but the sample size is limited. Portable XRD systems exist for field use, though with lower accuracy. And we always rely on careful calibration and stress-free reference samples to make sure results are trustworthy. So in short, XRD lets us non-destructively probe both the stresses locked into the material and the crystallographic textures that influence their performance. The second application of XRD, which I think is interesting, is thin films and semiconductors. The foundation of thin film analysis is the symmetric 2 theta omega scan. Here the Bragg planes remain parallel to the sample surface, which lets us pick up details like crystalline phases, lattice parameters, the degree of crystallinity, and even subtle strain or stress through peak shifts. With this technique, we can distinguish between different kinds of films, epitaxial with a single orientation, textured, polycrystalline, or amorphous. When we want more surface sensitivity, we use grazing incidence XRD or GIXRD. By lowering the incident angle to less than a degree, we reduce the penetration depth of the X-rays. That makes it ideal for studying very thin films where substrate peaks usually dominate, as well as nanostructured coatings. And in the semiconductor world, XRD is central for the epitaxial layer characterization. For example, in gallium arsenic or indium gallium arsenic systems, we can track strain, composition, and dislocation. In these stacks, in these systems like gallium arsenic system, XRD helps us profile layer thickness and composition. With INP and SIGE systems, it even supports high frequency and CMOS device development. And in gallium nitride and aluminum gallium nitride, which are vital for LED and power electronics, XRD quantifies dislocation density and strain engineering. So whether it's determining how well a film has grown and probing its defects, or confirming the structure of semiconductor devices, which is extremely important, XRD provides a non-destructive window into the materials that are only few nanometers thick. Right, so the third application that we'll be looking at is phase identification and quantification. First, let's talk about the qualitative side, phase identification. Think of an XRD pattern as a unique fingerprint for every crystalline material. No two are the same. The process is straightforward. We measure the diffraction pattern from our unknown sample, which gives us a set of peak positions of 2 theta and intensities. We then compare this experimental fingerprint to massive databases like the ICDD to find a match and identify the phases present. This is incredibly useful in pharmaceuticals to distinguish between different polymorphs, or in geology to identify minerals in a rock. But often just knowing what's there isn't enough. We need to know how much of each component is present. This is quantitative phase analysis, or QPA, highlighted here in the purple box. There are several ways to do this. A common approach is the reference intensity ratio RIR method, where we compare our diffraction intensities to a known standard, like corundum, or to calculate the weight fractions. For more accuracy, we can use methods which basically use internal or external standards. However, for complex multi-phase samples, like the one shown in the diagram, the gold standard is Rietveld refinement. This is a fantastic computational technique where we don't just look at a few peaks, we model and fit the entire diffraction pattern. It allows us to calculate the precise amount of each crystalline phase, and it's robust enough to handle the overlapping peaks you see in that resulting XRD pattern on the bottom right. As you can also see that the field is evolving. We are now leveraging machine learning and AI to automate this entire process, making phase analysis faster and more scalable for high throughput applications, from quality controls to new material discovery. So in short, XRD allows us to take complex mixed materials, and using these identification and quantification techniques, we can precisely determine its chemical recipe, which is crazy.
Now looking at how we address these challenges. On the practical side, high-resolution optics, fast detectors, and optimized scanning improves accuracy, while better sample prep, standards, and AI-assisted processing reduces bias and speed up analysis. For the future, we see an in situ XRD for real-time studies, faster synchrotron, and XFEL experiments, and machine learning for automated phase identification. Advanced and portable diffractometers, 3D 4D imaging, and open fair data pipelines are also shaping reproducible ML-ready workflows. This slide highlights the main challenges in X-ray diffraction. First, instrumental limits like detector resolution speed, limited lab source brightness restricts fast or nanoscale studies. Second, sample issues such as preferred orientation, size broadening, and weak scattering from amorphous or light element material causes biases and errors. Third, data analysis bottlenecks include overlapping peaks, background subtraction problems, and the need for expert-driven Rietveld field refinement. Finally, practical challenges like high cost, limited synchrotron access, slow turnaround, and inconsistent metadata reduces reproducibility and data reuse. Altogether, these hurdles affect accuracy, reliability, and accessibility of XDR experiments. So, to overcome these challenges, future trends now focus on improving instrumentation, smart data analysis, standardized, fair workflows.